Yeah, thank you for these papers. I was thinking a lot about just something that Grace mentioned very briefly about how noise comes from the agents sometimes. The noise isn't always an environmental problem. And that seems like introspection is kind of with that same question. So like, to what degree do you think the literature has already like distinguished, I guess, noise that the agent produces from the signals it wants to focus on? Does that make sense?
Yeah, honestly, I can't comment on what the literature has said. I'm still just kind of digging into this topic in terms of literature search and that kind of thing.
Well, I mean, do you have any like thoughts specifically connecting to that comment of Grace's?
Sure. So, I mean, I gave you this whole kind of laundry list of different measures that we might look at, and I kind of had it separated into these three categories. But some of these were related to the learning process, some of them were related to the environment, and to the experience and that kind of thing. And that's a bit misleading because you're absolutely right. These things are all kind of tied up. The environment affects how the robot behaves, it affects the learning process. Those learning algorithms affect the kinds of decisions you make about what kind of data you want to acquire, these kind of things. So they're not that well separated, and they are kind of bound together. And so I still need to figure out exactly how much differentiation I can get with those.
Hi, I have a question about, from the introspection perspective, have you seen how it actually contributes towards increasing or improving the rate of convergence of the overall model to an optimal agent?
I haven't done experiments yet, so this is kind of the next step, is to get this up and running and start looking at really how this makes sense in the decision-making processes.
Okay, slightly more extended question. I'm not sure to what extent people would agree that the robots generally are going to operate on a OODA loop type principle. I mean, but along those lines, there's effects of uncertainty and novelty. Uncertainty generally is going to operate at the side level where you have to make a decision. I don't know enough about either what the object is or exactly where I am, so I may have to explore, versus novelty that's generally going to appear at the observed level and cause you to reorient. You'll have sort of an immediate response. So my question is, with those two elements of uncertainty and novelty, do you have to do special things in order to deal with it?
I'm not sure that I'm entirely clear of how well those two concepts are separated.
Well, uncertainty is, you're approaching an object, you don't know what it is. And so you either have to make a decision to explore more or to circumvent it, or whatever you're going to do, whereas novelty, there's something that appears suddenly, you have to react to it. So you have to avoid collision with it, whatever. That sort of.
Are we talking about the same object, just uncertainties prior and novelties posterior?
Okay. So then what's the question then with those two, if you have those two?
Just how is that going to impact your reasoning processes? I mean, like, do you have breaks in the induction? Do you like switch off to an entirely different path?
Right. Yeah, honestly, I don't think I can give you a great answer on that. Ideally, I would imagine like, kind of what I'm trying to argue for too is that you don't treat these things specially. You allow your system to make all sorts of measures and models of what's going on. And then, you know, I'm coming from a reinforcement learning background, and so it takes these bits of data, whether they're internal or external, or uncertainty or novelty, and you simply take them as part of your state space, you take them as part of your model, and you figure out the best policy to act in those situations. I don't want to hand code any sort of particular way of responding to either of those.
With that, I just want to mention, I think part of what Ray was thinking about was if you rank your programs in order of likelihood, that I think you're talking about sort of like a black swan event, and that if you have a full ranking of programs and you weight them, you may be able to answer that question. It's sort of like a Laplacian thing, and maybe you can talk about it afterwards. I can show you some of what Ray was writing about in terms of the problem of the black swan and how you can anticipate it as part of a coherent thing. It's not a separate thing. You can,
yeah, that makes sense. It's the solution of the black swan or white raven problem. And actually, Hutter has a paper about it. It's similar, but the thing is, there's a lot of background knowledge, right? So you know a lot of things about animals, genetics, how they can mutate. So you can actually predict that there could be a mutation somewhere, and you could have a bird with a different color, right? So if you're going to have that problem of induction, if and only if you have no background knowledge whatsoever.
one other quick thing is that since Ray, really what Ray was interested is measurement, so that you could actually measure into the future rather than just measuring here, measure here, and wait, you know, the likelihood of these future things. And by the correct weighting, you can have some information about a black swan. And he did a lecture on that. It's at the website. I'll give you the website.
So, Arthur, I have two questions for you. The one is, how does your approach change if the features are not independent? Have you done any work on that? How would it affect that? And the second question is, do you have any practical examples, any tests that you actually ran, and what kind of speed improvement you actually found, if you have done any kind of practical tests?
So, concerning the independent features, so the math actually shows that there is always such a set. If an object is, or if a string is incrementally compressible, then there is such a set of features that are independent. Of course, the set is not unique. It's like it makes an orthogonal basis, but the basis is not unique, like in linear algebra. You can have a different set of features that would also be mutually independent, but they might be dependent of the first set of features that you have chosen. So, of course, the number of possible features is infinite, but such sets do exist that are independent of each other. I mean, intuitively, they make up different sort of equivalent representations of your object that you're describing. So, and the second question was about the practical implementation. Yeah, I quickly referred to my last year's AGI publication, where I actually executed all 1, 2, and 3 state Turing machines and generated billions of strings, and then applied a similar method that incrementally compresses them, and it arrives at almost the shortest descriptions of them if you measure shortest by resource-bounded level complexity. And yeah, it does seem to work and much faster than if you try to look for a solution in a non-incremental way. So yeah, in a sort of, I mean, it's not kind of realistically useful now, but it does work in practice, and yeah. So
I have a question for Mr. Arthur. Do you think, could you relate in any way the Fourier decomposition and the orthogonal basis that you just talked about? Is there any relation whatsoever?
the Fourier decomposition, well, is it possible to make a Fourier decomposition of the space of programs?
Something like that? Do you think it's relevant?
Well, I mean, how can I relate it to something that doesn't exist? I mean, it is a type of decomposition, and it decomposes the problem, and that's why it speeds up Levin search so by such a big amount. To make it really useful, you'd have to speed things up even more, and I pointed to the possibility. Let's say you have the whole universe encoded as binary string. And in order to find a description of it, you wouldn't try to find a program that generates the description of, generates the encoding of the whole universe. You would just start describing, you know, this little object and then that little object. You basically partition your whole string into little pieces and try to compress them piece by piece.
Piecewise.
Piecewise, yes. And how to do that, and to derive theoretical guarantees for that, this will be a very interesting future work, and it would speed up things even more.
I don't think that can work in general, can it? I mean, if you have a general program, you can't, in general, decompose it hierarchically into pieces. I mean,
Well,
that's
whether you
special
can do it
case.
hierarchically in terms of first finding a partition of it and then go, I don't know, because this is future work. But
Sorry,
you can do it incrementally.
sorry, but we already have done such work with the hierarchical decomposition.
We have what?
We have already done such work, and we have publications on this. And we also obtained similar speed up as in your case, but not in an incremental way. So it's not absolutely future work. It's at least partially already had been
Hierarchical
done.
but not incremental?
Yes. Well, it's not incremental in your sense, but I guess we can discuss it during.
I'm curious to find out about it. You know, I don't know what you mean.
Yeah, we will discuss it during coffee break. We have much more questions.
My question to Eray.
All right.
In terms of the physical limits of induction, you provided one number, 370 something. And you said that represents the limits for this universe. And you say this universe, which parameters of this universe are relevant for that computation? Can you provide some insight?
So you have to see the paper. It explains there. It's referring to the physical limits of computation work. Margaret Levitin bound, and that's stuff the Seth Loy's work. So there are some physical measures, and it tries from there. It's in the paper. It's
Is it like, the size of the universe and things like that?
No. It's about the how many computational operations you can make with given for a fixed energy. It's something like that. Which is I can't really explain it without equations.
So if the universe is not finite, what then?
Universe is not. It's not relevant to us because there is we're not going to get any signals from outside of the
No, I know.
universe.
Just maybe
So it doesn't matter.
energy may be created.
Yeah. So, but it doesn't matter because no stochastic source you can observe will lie beyond the observable universe. So it really doesn't matter if the universe is infinite in extent or not. So that's pretty obvious, right? Because Einstein's theory is correct.
Okay, next
Could there
question.
be quantum entanglement from things beyond
beyond our observability due to the speed of light?
Yeah, so you're not going to, that still isn't going to matter. It could contribute to the stochasticity of the phenomena, but you're not going to get any order out of it. So it's still the same thing. It's not going. It won't matter. Okay.
Question for Dr. Arai. Did I say that right? Arai? Well, anyway, I'm not used to data information coming out in units of meters. What towards the end again, from the famous number of 400 bits, it's going to be famous shortly. You said if the volume is 1 meter.
Huh?
You said if
logical volume
of the bit string describing the universe, the logical volume of what?
It means any computer that's going to have a space-time volume of computation that's smaller than 1 meter cubed times second, right? It's not for very large computations, but for reasonably sized computations, that is the case.
So you're setting a smallish limit?
Now it's okay. So the logical volume of computation was with respect to the stochastic source there, I think, if I remember correctly, and that means we're not considering very large sources. We're not considering very large, physically complex sources actually. But so there's a condition. If you remove that condition, that number could change there. I didn't really analyze. It's just an example, right? So it's just an example to show that you can obtain some numbers if you substitute them. So it's not just theory, but it's a theory that's applicable to the real world.
This is a question for you, right? You introduced the concept of stochastic logical depth.
Yeah.
Extending Bennett's concept, and you say that it involves accurately simulating the stochastic source.
Yeah.
Can you say more on what you mean by accuracy?
Well, what do I mean by it? Well, since induction will work only with computable PDFs, right? So that if it's computable, it means you can simulate it exactly. Accurate means exact in this context.
How is it defined?
Exact means like it yields exactly the same probabilities, man. So it's yielding, of course, computable reals, right? And yeah.
We have time for a few more questions.
But that's maybe not so obvious. I thought it was very obvious, so.
My question is to Ms. Solomonov. I'm just wondering, what was Ray's take on transfer learning with respect to Solomonov induction?
You're talking about transfer learning? Can you be a little more specific?
Incremental learning, the 89 paper and.
Even like the concept nets?
No, it's the stuff I talked about the other day.
Let's see, well, he would have, that you, can take parts of programs and pieces of concepts and add them together. You can combine them to solve a future problem and use them as building blocks for problems. And he would use that with Levin search, to quantify steps in the learning, so that you might have, you might start with one program that you found, and you can find regularities in that program to build, and say this guy finds one program and this guy finds a program in a certain time length, in like a computational cost time length, and you can take these different parts of programs, or, and maybe combine them into a smaller program. But you would wanna keep the idea of ranking of the different programs, because some of the parts of the programs might end up with different size, ratio, different sizes than other ones that we combine. I'm afraid that's not very clear, but it's, the idea is to combine the different bits of things and to rank the different bits of things in a hierarchical order. And with Ray, I think one thing that frequently gets left out is that he's really interested in ratios of things, so that you don't just necessarily find the smallest thing. You're not just looking for an Occam's razor, which is why you can combine different, as long as you can kind of measure the different concepts to combine them and then you can find smaller, but you want to keep a ranking so that you can go back to a lower concept. And if, say, this concept didn't work, you could go back to an earlier thing and build from lower steps. We can talk more about it, and maybe I can show you some of the lectures that he had, because he can explain it in a less poetic way.
May I explain? It's my philosophy. It's Solomonov did say that incremental learning is absolutely essential. He never suggested that a non-incremental thing would reach high levels of intelligence. And that's why he explicitly wrote this as an important open problem. And he had many suggestions. And the other thing that you talked about is, in the standard theory, we call that base factor, right? So that's how, that's